After this very nice talk about topological states of matter as has been found in solid state materials, I will switch topics slightly, so I will give you a view on this topic from the cold atom community perspective. So we hope that with our ultra-cold atom setups we can provide complementary measurements and help getting a better understanding of, in particular, interacting topological many-body states. So this work was done in the group of Emmanuel Bloch in Munich. I recently moved to Collège de France in Paris, but all this work I'm talking about today was basically my PhD work in the group of Emmanuel Bloch. So let me first introduce the team. Without all these people, it wouldn't have been possible to do it. So of course I would like to thank my supervisor, Emmanuel Bloch, our postdocs that now got all very nice positions in different places all around the world. And in particular, I would like to thank Markus Atala, who was the main PhD student with me during all that time. And of course our theory collaborators, the team working on the gauge field, and also on topology in one-dimensional systems, which I will be not discussing today, but which we have also done during that time. So let me go one step back, and I will start from a more basic introduction into the topological properties of materials. And I just want to remind you briefly about why it was so fascinating to find the quantum Hall effect in two-dimensional electron gases. So we all know that in a three-dimensional Hall bar geometry, if you send a current through your Hall bar and you measure and you have a perpendicular magnetic field and you measure the Hall voltage perpendicular to the current, you get a linear curve as a function of the applied magnetic field. And this can be used to measure current carrier densities and so on. And it has been found in the 80s that if you perform the same experiment with a two-dimensional electron gas that is cooled down to very low temperatures and the magnetic field is very strong, these quantized plateaus emerge. And you all know this is the famous discovery of the quantum Hall effect. But just as a reminder why it was so remarkable to find this is because all these plateau values, they are just related to natural constants and labeled by integer numbers. It's as simple as that, and remarkably, these values of the plateaus do not depend on the microscopic details of the sample. So different samples might have different shapes of these plateaus, but the values occur always at the same positions. And what's remarkable about this simple relation between the plateau values is that you can label them by integers and these integers essentially just characterize the topological properties of the individual bands that are filled with electrons. And well, this is a comparison to how you can label geometric objects with simple integer numbers by counting the holes that you have in the surface of these geometric objects. And I will show you from this more basic point of view how we can characterize energy bands in terms of integer numbers. So this is the Chern number that is the topological invariant that characterizes each energy band. So the outline of my talk will be as follows. I will first introduce the technique we use to engineer artificial magnetic fields in our setups. Then I will briefly show a few experimental results that we obtained in this context to give you an idea about what we can measure in cold atom systems. Then I will discuss the Chern number measurement that we performed in these artificial gauge fields and some future prospects that we might be able doing with these setups. So in our labs, we start with a cold gas of atoms. We trap them in various potentials, but they are neutral. So in order to study magnetic field effects in the spirit of the quantum Hall effect, we have to find different ways how to mimic magnetic field effects. So we engineer what we call artificial magnetic fields or gauge fields in our system in order to mimic charged particles in magnetic fields, the behavior of charged particles in magnetic fields. And there has been a long history about how we could do that in our setups. For example, there's one way of doing it by exploiting the equivalence between the Coriolis force and the Lorentz force. So when you set a gas into rotation, you imprint angular momentum onto the gas, and if it's in a superfluid state, this shows up at these quantized vortices in the gas when you look at it after time of flight. Now, a different technique is by engineering spatially dependent couplings between different internal states of the atom. This is in the spirit of engineering artificially a Aharon of Bohm phases. So when the particle moves around in your parameter space, it picks up a finite phase which is reminiscent of the Aharon of Bohm phase a charged particle picks up in a magnetic field. And here you also see this vortices appearing in the gas, which show that we have an artificially magnetic field engineered. So in these setups, it's difficult to reach very strong field regimes, which we need if we want to move on and study strongly correlated topological many-body states in the spirit of fractional quantum Hall states. So there have been several ideas how to do that in optical lattices. It seemed easier to reach the strong field regime in these systems, and there are several techniques on how to do that. For example, by shaking the position of the optical lattice or by modulating the depth of the optical lattice, and engineer also Aharon of Bohm-like phases when the particle tunnels around in this lattice. And this has been done in triangular lattices and hexagonal lattices, where it was been shown that we can implement also the Haldane model. In hexagonal lattices, what I will be discussing today is very similar to these techniques. And more recently, there have been other techniques in synthetic dimensions, which is essentially like a two-dimensional optical lattice that you replace one of the two axes by internal states of the atoms. So you have a 1D lattice here, and the second axis are different Zeeman levels of the internal structure of the atom. And then also by coupling these different states, we engineer phases such that when a particle moves around in this parameter space, it picks up a finite phase that can be interpreted as an Aharon of Bohm phase. And there's a lot of work about these topics, so I cannot mention all the people here, but there are many review papers if you want to know more. So how does our setup look like? So we start with a cold gas of atoms. In our case, we work with bosons, so we start with a Bose-Einstein condensate, and we load it in periodic potentials that we create by standing waves, using lasers, or by interfering laser beams. So we trap them in this periodic potential, and we can describe the dynamics using the Hubbard model. So now this is a very simplified version of it. We neglect interactions for now, and we consider only a single spin component. So this works for fermions and bosons. So all the dynamics is characterized by this tunnel coupling between neighboring sites. So if we think about having electrons instead of neutral atoms on this lattice, and we apply a magnetic field, what happens is that particles that hop between neighboring sites pick up a phase that is determined by the vector potential that is generating the magnetic field. This is the so-called Peierls substitution, so I will typically refer to this phase as Peierls phase. And this is what we have to engineer in our lattices, because typically our tunneling between neighboring sites is real. So we have to find different ways to engineer this phase factor if we want to mimic the physics of charged particles that are moving in this periodic potential. So if we manage to engineer these phases and the particle hops around a closed loop, it picks up a finite phase, which is simply the sum of all these phase factors here, and it's directly related to the magnetic flux that is piercing one unit cell. And now it's easier to see how ultracold atoms and optical lattices might be well suited to reach the strong field regime, because if we manage to engineer these phases, which are naturally on the order of 2 pi, we enter a regime where the magnetic flux per unit cell is on the order of the magnetic flux quantum. And these are very strong magnetic fields in typical solid-state materials, and this would be on the order of 1,000 Tesla if we compare the scales. So all we need to do is to engineer this Peierls phases when the atoms hop between neighboring sites. And I will explain how we do that on a very simple model, so I consider only a double wave potential. And our starting point typically is that we apply a potential energy offset between neighboring sites, which is larger than the tunnel coupling between the two sites. In this case, atoms are essentially pinned to site A, and they cannot hop to the neighboring site because the energy they require is too large. Now, in this case, we can restore hopping between neighboring sites by applying a periodic modulation to the lattice. So we shake this lattice well up and down periodically with a frequency that matches this energy offset. So the atoms can absorb photons and re-emit photons into the laser field and overcome this energy barrier here. And now if we go through Floquet formalism, because we have created or engineered now an explicitly time-dependent Hamiltonian, we can derive an effective time-independent Hamiltonian that describes the stroboscopic dynamics of this system, or the long-time dynamics of this system. This works only if this energy offset is much larger than all the other energy scales. So we have to drive with a frequency that is large compared to the hopping here between neighboring sites. So here what happens is you see that the tunneling becomes renormalized. So it depends on the modulation strength that you apply and the frequency with which you shake the lattice. And we have this complex factor appearing here, which is related to the phase of the driving field that we apply to the atoms. So if we can make this phase vary across our 2D lattice, we can engineer a situation where the atoms pick up a non-zero phase when they perform a closed loop on the lattice, which is then directly related to the flux piercing 1 unit cell. So if we move on to a two-dimensional geometry, what we can do is we can apply a linear potential gradient. So we have a linear potential energy offset that is delta between neighboring sites. And now we shine in 2 laser beams that are finely tuned to all our atomic transitions. So it's simply a potential that is varying in time because they have 2 different frequencies. But if this frequency difference depends on the energy offset between neighboring sites. So we tune the frequency difference to match this energy offset. So these 2 beams interfere. They create a running wave here in this geometry diagonal to the 2-dimensional square lattice. And here what's shown in this shaded gray area is the phase of this running wave at a particular point in time. So you see that the phase varies linearly across the lattice, which means the phase advances and changes from site to site. And now since we have the laser-assisted tunneling only along x here, which is the direction of the initial linear potential, we only engineer phase factors on this red dashed bonds. So we have real tunneling along the y-axis and complex tunneling along x. And since it's changing from bond to bond, this allows us to engineer non-zero flux, which is the projection on this of this wave vector difference onto this axis here. Okay, and it's in principle it's tunable. So if we change the angle between those 2 beams, or we change the wavelength, we can tune the flux this piercing wavelength. So it's slightly more complicated than that because it also depends on the potential that we use to inhibit tunneling in the first place. And it's not so easy to generate this linear potential here due to technical reasons. So we have studied several different setups where we have engineered staggered flux configurations that average out to 0 in this case, which is interesting by itself, but I will not discuss it today. This geometry can be used to generate a spin-dependent flux. I will say a bit more about that later. And it was used by 2 different groups to engineer homogeneous fluxes of pi over 2 and pi. And this is the Hamiltonian we have in the end. So this is the famous Hofstadter model, where we have complex tunneling along one direction and real tunneling along the other. I will say more about this later during the talk. And this is a more complex configuration that we use for the data that I present during the talk, but I will not go into the details of that. What's important is that it's independent of the internal structure of the atom, so we can apply it to bosons as well as fermions. And here all the data I present is measured with bosonic atoms, here rubidium-87. Okay, so let's move on to some of the experimental results. So the easiest geometry that we were able to study in the presence of a homogeneous flux is a so-called flux ladder. We can engineer superlattice potentials such that tunneling on every other bond is suppressed. So we isolate these ladders from each other, and they are subjected to this homogeneous flux that is piercing each ladder, but we can consider each ladder individually. And in the end, our observables are averaged over all ladders, so we have a full array of ladders, but we consider the dynamics is easy to describe by looking only at one ladder each time. And it's predicted that it is in this kind of configurations, if we prepare the ground state, there are chiral currents present in the system. This is reminiscent of the Meissner effect of a type 2 superconductor. So we have currents pointing upwards on the right leg, let's say, and in the opposite direction on the left leg, and there are no currents on the rungs. And what we can do is we can measure these currents by projecting the ground state wave function that we have prepared in this system onto isolated double wave potentials along the direction of the ladder. So we project this wave function onto this configuration where the dynamics only occurs between double waves, so between these two sides. And you can show that the amplitude of this current that you have present in the wave function directly relates to the oscillation amplitude of Josephson oscillations between the two sides of this double wave. And we can resolve them individually on the right and left leg and extract the chiral current of our wave function. And if we do that as a function of lag-to-rung coupling, this is what we see. So we can identify two different phases, which are like the vortex phase and the Meissner phase in a type 2 superconductor. This is a bit unconventional to tune the lag-to-rung coupling as opposed to tuning the external magnetic field. So this is the curve that you are more used to see if we talk about type 2 superconductors, but these are calculations for the exact same system, and it shows the exact same behavior as for type 2 superconductor. So the chiral current that we have screens the magnetic field in the Meissner phase until we hit a critical point for the external magnetic field, and we have vortices present in this current structure, and the chiral current decays to zero. Something else to measure more directly the strength of the artificial magnetic field that we have engineered, we can partition our lattice into these 4 side square plaquettes. So here now you should think about a lattice that consists only of 4 sides. Again, we have an array of it, but we can isolate them from each other and consider the dynamics individually only in this 4 side square plaquette. And we initialize the system by preparing a single atom in this 4 side lattice configuration. So this is a single atom delocalized over these 2 sides, and then we suddenly quench the system and switch on the magnetic field and look at the dynamics. So without the magnetic field being present, if we let this atom tunnel to the right side, we would expect to observe Rabi oscillations between the left and right bond. But in the presence of the magnetic field, we expect that there's also some non-trivial behavior perpendicular to that, which is reminiscent of some cyclotron orbit-like behavior in our lattice. So this is the data where we track the mean atom position in the plaquette. So the atom starts here on the left bond, so 0 means it's delocalized over the left bond. It starts to tunnel to the right. Rabi oscillations would show up simply as a line here. They will tunnel from the left to the right side. But here we see this orbit-like structure, which is reminiscent of a cyclotron orbit. And from this dynamics, we can fit the value of the flux that we have engineered in our system. I told you that we engineer flux of pi/2. It's not exactly that, but this is because the way we engineer the artificial magnetic field is purely geometric. And when we isolate or partition our lattice into these minimal versions of only 4 side square plaquettes, it moves the minima of the lattice slightly closer together, which reduces the phase, which is purely geometrical, and thereby reducing the flux that we engineer. But if we go back to a fully coupled 2D lattice, it would be still pi/2. Now, in order to engineer a spin-dependent magnetic field, we can make use of a magnetic field gradient to engineer the linear potential that inhibits tunneling in the first place. So this is what I've shown you before. We can use this configuration to engineer a homogeneous flux through our square lattice. But if you go through the math in deriving the effective Fouquet Hamiltonian, it turns out that the phase we engineer depends on the sign of the energy offset. So if we reverse this linear potential, we engineer the same strength of the magnetic field, but it points in the opposite direction. And if we use a magnetic field gradient to do that, we can load two different states of the atom in our lattice, which are here labeled as spin up and spin down, but it's two different Zeeman states which have opposite magnetic moment. So it's the same magnetic field gradient that they see, but the potential they see is points in opposite directions. So if we load these two spin components in the same lattice, they see the same strength of the magnetic field, but pointing in opposite directions. And this is the simplest version of the quantum, how to engineer the quantum spin Hall effect in our system. So you have seen in the previous talk, the quantum spin Hall effect. It's just two copies of quantum Hall system, and in the simplest case, where both spin components see the same field but pointing in opposite directions. And what we can see here is we can look at the spin Hall effect in the small plaquette potentials by initializing a single atom on the lower bond. We let it tunnel to the upper one, and if it's spin polarized, we obtain a certain non-trivial oscillation amplitude perpendicular to that, and this amplitude depends on the spin mixture that we prepare in our setup. So this is the spin Hall effect on an optical lattice that we observed. Okay, so now let's move on to the topological properties. And we go a bit fast on that because I don't have so much time. But so to remind you how we can characterize the topological properties of an energy band is we describe it in terms of Chern numbers. The Chern number is the integral over the Berry curvature in momentum space. And this is directly related to these plateaus that arise in the 2D quantum model. So the Berry curvature that describes the geometric properties of the band is given here, where U is the periodic Bloch function we prepare our atoms in. So this is for atom at momentum k. We have this Berry curvature dependence, and if you integrate it over the full momentum space, you obtain the Chern number of the corresponding band. And more recently, there has been a lot of work in characterizing this Berry curvature in momentum space. Here is shown an image where they were able to map out the Berry curvature in the first Brillouin liaison of this hexagonal lattice. But so far, this was performed in systems where the Chern number of the total band is 0, while we are interested in studying bands where this Chern number is non-zero. Yes. So we want to measure the Chern number of a band with non-zero value, and for this we have engineered the artificial magnetic field, which is described by the Hofstadter model, and you know how the single particle energy spectrum of this model looks like. So here is the energy of the lowest tight binding band as a function of the flux piercing the unit cell, and if the flux piercing the unit cell is a rational value, we see that this lowest tight binding band splits into several subbands. In our case, it splits into 4 subbands, and the lowest band has a Chern number of 1 and is topologically equivalent to the lowest Landau level. So how can we measure the Chern number in our setup? This is motivated, very similar to transport experiments that are done in solid state setups. We apply an external force to our atomic cloud and see what happens in situ. So we directly look at the position of our cloud and look at the center of mass motion after applying the external force. So in the direction of the force, semi-classical dynamics tells us we have a band velocity that's captured by the dispersion of the energy band, but if the topology of the band is non-trivial, we also obtain a velocity component perpendicular to that, which is proportional to the Berry curvature at where the wave packet is centered in momentum space. So we obtain this non-trivial behavior that if we look at our atomic cloud and we apply a force to it, we should see that it gets displaced perpendicular to the applied force. And if we consider a filled lowest band, we can isolate this anomalous contribution perpendicular to it because the contribution from the band velocity averages to 0. And we are left with a center of mass motion perpendicular to the force, which is simply proportional to the Chern number. So this can be done with fermions by setting the Fermi energy within a spectral gap, or in our case of bosons, we consider an incoherent distribution when the temperature of our gas is larger than the bandwidth of the lowest band, but still small compared to the gap to the neighboring band. So this is what we would expect if we prepare all the atoms only in a single band, in the lowest band of this artificially engineered Hofstadter spectrum. And if it's imperfect, our initial state preparation, and we have atoms also in higher bands, the slope that we expect is reduced. And this you can simply understand because the sum of the Chern numbers of these 4 bands has to give 0, which means we have some bands with negative Chern number which would show up as a motion of the atoms that goes opposite if we apply the same force. Okay, and this is what we see. So we have we expect a reduced slope. And when we look at the mean position of our atom cloud after applying the force, this is what we get. So this is the differential shift, meaning that we look at the position of our atoms by applying plus magnetic flux minus magnetic flux to account for possible drifts during the performance of the experiment. So this is what we call differential shift, and this is one image that we have obtained by subtracting them for positive and negative flux. And you see that the 2 clouds separate perpendicular to the force which is applied along this direction. And if we fit a value to this data, it's close to 1, which we expect from theory. The error bars are still rather large, and you see that they deviate from this linear behavior, which is due to transitions to higher bands during the dynamics. But now if we look for longer time scales, we see that it saturates very rapidly. We can also reverse the force and see that it behaves the same. We can perform the same experiment by switching off the magnetic field or using a staggered magnetic field, which has a trivial topology, where we see no dynamics occurring in this direction. But if we compare to numerical simulations, which are shown in green, we see, and they take into account these transitions to higher bands due to Landau-Zener transitions, we see that this cannot explain this rapid saturation that we see in experiments. However, what we can do is we can measure the population of the different artificially generated Hofstadter bands during the dynamics. And when we do that, this is what is shown here, or here what I call the filling factor, which takes into account the different populations in the different bands, we see that this saturates to 0 on a very similar time scale. And when this factor reaches 0, it means that we have infinite temperature state. All the bands are populated homogeneously, and we do not expect to obtain any deflection perpendicular to the force anymore. So even though we still have to understand what's this repopulation dynamics during our measurement, we can use this information and in order to fit our data and extract a value of the Chern number of the lowest band. And this works very nicely. It's very close to 1, and the error bars are much smaller in this case. So the dynamics is consistent, but we still have to figure out what's happening during the dynamics. And with this, I would like to conclude. We managed to realize the Hofstadter model and the Hamiltonian underlying the quantum spin Hall effect using laser-assisted tunneling in our optical lattice. We have performed measurements of topological invariance in 1D and 2D, which 1D I didn't present today. And ongoing work is on topological charge pumping, which can be used to measure topological or higher dimensional topological invariance in reduced dimensions. So Hannah will talk a bit more about that in the following talk, or not? No? And so ongoing challenges are to understand the repopulation dynamics, to understand the heating that we have in our system, to figure out how we can include strong interactions and to engineer strongly correlated topological many-body states, which we hope to study in this setup. And just to mention, this flux value of 1/4 seems to be very well suited to start entering this topic, because it has, we can use it to compare to existing models. So for a flux of 1/4, we can still compare to continuum wave functions like the fractional quantum Hall-like states and try to figure out what's the best observables to look at them. But there are also novel topological many-body states predicted, because the dispersion of the lattice is already important for this large magnetic field. And if we can manage to combine it with all the new recent experimental techniques that were developed in our community, we have many possibilities in studying the dynamics of these systems by looking at edge state dynamics, out of equilibrium dynamics, study excitation spectra, or measuring correlation functions, and many more. Thank you very much for your attention.
So thank you for a splendid talk, which is now open for questions.
Yeah, sure. So I had a couple of questions, if that's okay.
Yes.
My first question was about your cyclotron orbit, the cyclotron radius plot. So I guess that's a semi-classical interpretation of what's going on, because I guess in principle, when you apply a field, then the correct quantum number is in the magnetic Brion zone, which doesn't actually really need to look like a cyclotron orbit at all.
Yes, well, the parameters are chosen such that it looks more or less like a cyclotron orbit, but you can think about it simply as an interference effect. So you have a single atom in this four-side lattice, and when it tunnels around in the lattice, it picks up different phases, so there are interferences going on, and if you choose the parameters slightly different, this orbit can have whatever shape. So it's not a real cyclotron orbit in this sense.
Does it contain an integer number of flux quanta? Because in principle, that's what it should contain.
Well, so it cannot really contain an integer number of flux quanta, right? Because we have only a quarter of a flux quantum per unit cell. So in that sense, no, but it's not a real cyclotron orbit.
Right. So my other question was about your Hofstad Hamiltonian. So you had a phase factor on just one part.
Yes.
Which, because in the phase factor, if I remember, it's actually the vector potential that goes into it and not the magnetic field. So,
yes.
So does that mean you've chosen a specific gauge?
Yes. Yes, exactly.
So you can actually tune the gauge for
yes.
the experiment?
And the exact gauge that we realize in our setup actually shows up in the momentum distribution. If we perform a time of flight experiment, we can see what particular gauge we have realized in our setup.
That's fantastic. Can you choose a symmetric gauge and then show that you get exactly the same results rather than the Landau gauge, which I guess is what you used?
In principle, yes. Yeah, if you find out a nice laser configuration that allows you to tune this gauge, yes. Yes.
Other questions? Steve?
This is bosons, but you filled a band as if they were fermions, because they're a particle bosons. Is that weird?
Okay, so the question was how we fill the lowest band, because we have bosons and not fermions. So in our case, the temperature is larger compared to the bandwidth, so it's more like a statistical mixture in the lowest band, where we populate all the different momenta. And we have checked in the experiment, or we have evidence in our data that it's more or less homogeneously populated. It's not a proof, but yes. So we can measure the momentum distribution, and it seems that it's more or less homogeneously populated. It would be a bigger problem if the band is more dispersed. But our band is rather flat, so this allows us to do that. Yes?
In the setup, it looks like you can change different staggered flux configurations and homogeneous flux configurations simply by changing the wave factor of the incoming wave.
Yes, so in this particular configuration that we used, I can show. Just go back to the image I've shown. So I briefly mentioned that the phase that we engineer depends on the sign of this energy offset. So if you now forget about these beams, and still we simply have a running wave diagonal across this lattice, and this potential instead of the linear one, we end up with a staggered flux configuration where the field is pointing out of plane here and pointing inwards on the neighboring stripe. One way to overcome this, which we used for the latest measurement, is to engineer spatially dependent coupling. So the coupling now is slightly more complicated, so we use more beams in order to couple neighboring sites, and this allows us to address red and blue bonds individually. And by doing that, we can decide to flip the sign here or not. So using the same laser configuration, we can have staggered and homogeneous flux present in the set.
So you really need a second set of lasers.
It looks more complicated than it is. It's actually only a single laser, but we have modulated side bands onto it. And this one is simply back reflected, so it's a standing wave, and this one is a running wave. So it's actually not that complicated. It looks more complicated than it is.
Further questions? So, may I ask one in that case?
Yes.
You raised this question about what's going on with the repopulation dynamics in this side shift extraction.
Yes.
You also mentioned earlier on that, of course, because your scheme involves a time-dependent steady drive, you really only define the energy up to modulo of the frequency attachment.
Yes.
Which means that there's no longer really any notion of lower bands or upper bands.
Yes, that's true.
Do you
So we
think
look at
that's-
one particular Floquet mode.
Right. So is that related, or have you tried to do repopulation calculations in that Floquet scheme and it still doesn't?
So what we believe right now is, because I totally neglected interactions between the two, between the atoms. So if they interact, it can happen that, so due to the nature of our interaction, they couple different Floquet modes. So they can go from Floquet mode 0 to 1, and then release some energy into 3 modes that we have present perpendicular to the lattice. So I only discussed the dynamics that was happening in the 2D lattice, but we have actually around 100 atoms per side. They're in these 1D tubes. They're very closely spaced energy levels, and they can release energy into these modes and repopulate higher Hofstadter bands by doing that. And currently we believe that that's the process that leads to the repopulation.
Any further questions? If not, let's thank Monika.